Hello, I'm Richard with EV4U. In this episode, we will discuss how to determine the size requirement of the battery pack. Determining the battery pack size in watt hours is one of the first steps in designing an off-grid power system. That's assuming that most will use a battery pack as part of an off-grid power system. Phones, computers, lights, fans, water pumps, hair dryers, electric bikes, electric cars, heating, cooling, cooking, washing machine, TV, and a multitude of other necessities are all items that require power. All of the items to be powered will represent a load to the battery pack. Some of the loads will be DC loads and some may be AC loads. The first step is determining and calculating the DC loads and the amount of time per day the load will be used. Start by making a list of all the items to be powered. Determine the power requirements of each item. Estimate how long each item will be requiring power during a 24-hour time period. Then determine the AC loads and the time they will be used during a 24-hour period. If the AC loads are powered using an electronic inverter, then they too are ultimately a DC load, as the battery pack provides power for the inverter. To calculate the DC load of the inverter on the battery pack, consider the following rule of thumb. A 12-volt inverter requires approximately 1 amp of DC input for each 10 watts of AC output. Let's look at an example. Assume a 100-watt AC load is being powered by the inverter. We divide the AC load in watts by 10. That would mean, in this example, that the inverter is drawing 10 amps from the battery pack. So how much DC power is that? Remember that power is measured in watts. According to Joule's law, power is equal to amps times volts. Multiplying the 10 amps being drawn from the battery pack by the nominal voltage of the battery pack will give the power in watts. The battery pack nominal voltage is 13.2 volts, and multiplying that by the 10 amps of current draw means that 132 watts of power is needed from the battery pack. Now let's look at a hypothetical example. We're going to look at some DC loads and the amount of time that we're going to require that load over a 24-hour period, and that will give us the daily total of watt hours. So let's say we have a total of 5 lights and they're 7 watts each, and we run it for a total of 4 hours. So 5 times 7, that's 35, times the 4 hours, that's 140 watt hours per day. A water pump, say it draws 8 watts. We use it for a total of 1 hour per day. That's 8 watt hours per day. Security camera, total of 3 watts for 24 hours. That's 72 watt hours per day. How about charging your phone? You got 2 phones at 24 watts each, 2 hours per day. That's 96 watt hours per day. How about a DC TV? 100 watts. Watch 2 hours of TV a day. That's 200 watt hours. So these are just some, hypothetical random examples of particular load and the runtime and then the daily total. Now let's look at some items that may represent an AC load. Say you're charging a laptop using AC, 70 watts for 4 hours. That's 280 watt hours. Or say you run a water heater for 1 hour per day at 1500 watts. Well, that's 1500 watt hours. So you're going to have a total of X number of watt hours of DC loads and X number of watt hours of AC loads. And in this example, we had 4,146 watt hours of DC loads per day and a total of 2,830 watt hours of AC loads per day. Remember, the AC loads, which are powered by the inverter, represent a DC load on our battery pack. To determine the approximate DC load, we refer to the rule of thumb I mentioned earlier. A 12-volt inverter requires approximately 1 amp of DC input for each 10 watts of AC output. So dividing the 2,830 watt hours of AC load by 10 results in 283 amps that the inverter is drawing from the battery pack. Multiplying that 283 amps by the nominal voltage of 13.2 volts results in 3,736 watt hours of load on the battery pack. Add that to the DC loads from above for an estimated 7,882 watt hours per day required to run the off-grid system. Once the daily energy requirements have been calculated, how many days do you want to power the loads without charging? For the sake of an example, let's assume 4 days of power available without having to charge. That means the battery pack would have to provide 7,882 watt hours per day for 4 days. The battery pack would need to provide 31,528 watt hours or 31.5 kilowatt hours in order to provide that 4 days of usage. Now that the size of the battery pack is determined, what is that going to look like? Well, based on the system requirements, I would recommend a 48-volt battery pack system. How did I come to that determination? Let's look at another rule of thumb. Another rule of thumb is that if your energy needs are less than 1,000 watts, you can use a 12-volt system. If you use between 1,000 and 3,000 watts, then a 24-volt system is a better choice. If you require more than 3,000 watts, then a 48-volt system is recommended. Let's look at the practical aspect. If the power requirement is fixed, then the current will be relative to our voltage choice. Remember Joule's law. Current is equal to power divided by voltage. Here are some examples. Assuming a load of 2,500 watts, what are the differences in current and wire size, as well as the cost of the wire, in regards to a 12-volt, 24-volt, or 48-volt system? Well, a 12-volt system with a 2,500 watt load requires 208 amps. 2,500 watts divided by 12 volts, that's 208 amps. 208 amps will require the use of a triple-aught wire at a cost of $7.47 per foot. And I based this on the wire cost from Home Depot, just to get a comparison. A 24-volt system with a 2,500 watt load will require 104 amps. 104 amps will require a 3-gauge wire at $2.58 per foot. A 48-volt system with the same 2,500 watt load pulls 52 amps. 52 amps requires a 6-gauge wire at $1.42 per foot. So you can see the decisions become easier when you have a big picture perspective. Remember too that a 48-volt system is more efficient, smaller, lighter, and less expensive than using a 12-volt or 24-volt system. Let's continue the design process of the battery pack. Here's what we know so far. We want a 48-volt system with 31.5 kilowatt hours of capacity. So again, what does that look like? Well, we know from a previous video in this series that the nominal voltage of a 48-volt lithium iron phosphate battery is 52.8 volts. But what is the required amp hour rate? Well, taking 31,500 watt hours and dividing by 52.8 volts equates to 597 amp hours. With an amp hour requirement of basically 600 amp hours, that's a big battery. However, there are options. For example, we can use 3 200 amp hour 48-volt batteries in parallel. Just for the sake of discussion, what if a 12-volt lead-acid battery were used to provide for the 31.5 kilowatt hour power requirement? In order to get 48 volts, we would need 4 batteries in series. Since lead-acid batteries have a usable capacity of only 50% of their total capacity, then 1,200 amp hours of total capacity would be required. Let's look at the calculation. 4 12-volt lead-acid batteries in series equals 52 volts if the batteries are new and fully charged. Using a typical 12-volt storage battery, lead-acid storage battery, with 200 amp hour capacity would require 6 strings of 4 batteries to achieve the required 1,200 amp hours. The big picture would be a battery pack with 6 strings of 4 batteries in series parallel together. That's a total of 24 batteries. Remember that lead-acid batteries only provide 300 to 400 life cycles versus the 3,000 plus life cycles of lithium iron phosphate batteries. Using series parallel arrangements, you can achieve the required voltage and capacity for your battery pack. Here are some additional considerations when designing and building a battery pack. The battery pack should be properly contained, especially in mobile applications. In addition to securing the batteries, the containment should protect the batteries from physical damage, accidental shorts, as well as the elements. Keeping the batteries clean is important also. Dust and moisture can build up and can create electrical paths that can cause shorts, frame leakage, and or discharge the batteries. I recommend checking and maintaining the torque on the battery interconnects. This is especially important in mobile applications. A loose connection will cause increased resistance. Resistance equals heat, and heat can cause a fire. With mobile applications, weight distribution is very important. Batteries are heavy. That weight should be considered in your layout and design. Lead-acid systems need to be vented. Very important, as they give off hydrogen gas while charging. Hydrogen gas is explosive. Note that hydrogen gas is lighter than air and will rise. With lithium batteries in series, make sure to check the manufacturer's information, as the BMS system may limit the number of batteries that can be used in a series string. It's recommended that if a 24-volt or 48-volt system is suitable, that a 24-volt or 48-volt battery be used instead of using 12-volt batteries in series. Remember to never charge lithium batteries at freezing or below. However, some have low temperature protection, and some also feature internal heating. The battery pack should be switched on the positive side, and all circuits should be fused. The shunt always goes on the negative side of the battery pack. Battery pack should be monitored, and there are a host of options available today. At a minimum, monitor the battery pack voltage, state of charge, as well as the current flow in and out of the battery pack. In a future video, we will discuss the different methods for recharging the battery pack. Now let's talk about an electric inverter, also known as a power inverter or frequency inverter. It's a device that converts direct current DC to alternating current AC. It is necessary because the battery pack provides DC power and some loads require AC power. Two common types of inverters are the modified sine wave inverter and the pure sine wave inverter. Pure sine wave inverters are generally more efficient and better for powering a greater variety of electrical items. They are recommended for most electronic devices, especially sensitive devices that need a clear, pure AC sine wave. A common specification for inverters is continuous power and peak power. For instance, I have a 4,000 watt continuous power pure sine wave inverter that is rated at 8,000 watts peak power. This means that it can run loads that total 4,000 watts continuously. This rating should be greater than the maximum AC loads in the system. Peak power rating is so that the inverter can handle momentary surge loads like refrigerators and air conditioning units. Regarding inverter selection, the inverter input voltage must match the battery pack, or vice versa. It also must be able to power the necessary AC loads. AC loads were discussed earlier in this video. Let's consider the AC load requirements in regards to the inverter. Add up the largest number of watts needed at any given time, AC loads, and then add 20%. For example, if 1500 watts are required to run a computer and microwave at the same time, add 20% to the 1500 watts, which is 300 watts. And 1500 watts plus 300 watts is 1800 watts. In this case, a 2000 watt inverter would work well. Remember, the AC loads which are powered by the inverter represent a DC load on the battery pack. To determine the appropriate DC load, we refer to the rule of thumb. A 12-volt inverter requires approximately 1 amp of DC input for each 10 watts of AC output. A 2000 watt inverter will potentially draw 200 amps from the battery pack at 12 volts. However, with a 48-volt system, it would only draw 50 amps. That means the wire and fuse must be sized for the specific load. It is recommended that the inverter be located relatively close to the battery pack. It is also recommended that the inverter be located in a well-ventilated location for proper cooling. Most inverters have an on-off switch located on the unit. However, many also offer a remote on-off switch. Some inverters also feature an internal battery charger. The unit in my cargo trailer conversion is a 3000 watt pure sine wave inverter with a 12 volt 75 amp internal charger. In our next video, we'll discuss solar arrays and solar charge controllers. I hope you enjoyed the video. I thank you for watching. Won't you please like and subscribe? And I hope to see you next time.